Hello, and welcome to SETI Live. I am Beth Johnson, Communications Specialist here at the SETI Institute, and apparently forgetting my name today. I am happy to be here, and welcome to everybody who is watching. Please let us know where you're watching from. Welcome to our new listeners on the SETI Live podcast version, available on most podcast platforms. Today, I am really excited. We get to talk about one of my favorite things, which is exoplanets. And from the time that we started, sort of working on these, exoplanets were a relatively new thing. We didn't have a lot of them. Now we have almost 6,000 confirmed exoplanets out there. And the stories, when they do come out in the news, are always sort of it's something wild and woolly and interesting going on. And this one is no different. This is about WASP-43b. And it is a gas giant, but it has weather. And they have figured out that it has weather patterns. So this is really cool. Joining me today is Taylor Bell, who is a researcher at the Bay Area Environmental Research Institute and the lead author of the paper talking about this amazing discovery. So thank you, Taylor. Welcome in.
Hi, thanks.
Thanks for joining me today. So let's kind of kick this off. So we found weather on our world. Is it habitable?
Unfortunately not, no. We measured the temperature of the planet as part of the study, and we clocked the dayside at like nearly 2,300 degrees Fahrenheit. So yeah, pretty violently uncomfortable place to live.
Violently uncomfortable. I like that. That's a good turn of phrase. Okay. So I said this is a gas giant. So we're talking sort of Jupiter sized. Why this planet? What made you study this one?
So this was part of a large kind of collaboration that was targeted for the kind of first year-ish of the JWST Space Telescope's lifetime. The objective being to do early release science with the objective of quickly demonstrating the capabilities of JWST to the whole community. And so different research areas got to observe different targets in different ways and kind of just stretch out JWST, see how it performs, and then publish that with the community so that we can all kind of learn from those early experiences. And so this target is WASP-43 was chosen because it has a relatively short orbital period. It takes its equivalent of a year is only 19 and a half hours long, which is that's total of the entire Harry Potter series. So you can binge watch Harry Potter while the thing goes around its orbit. That means that we can feasibly observe the planet for one entire orbit. And when I say observe the planet, this planet orbits very, very close to its star. It orbits less than about 1/25th the distance that Mercury orbits our sun. So it orbits just extremely close to its star. So it's just flying around there. And we can't separately see the planet from the star. We just see one combined thing. But we can observe the whole system for 20-ish hours and see the changes in brightness as the planet goes around. And so, yeah, the objective of this was kind of twofold. One, test out JWST's performance for like staring at a single target for 20 hours. How precisely and continuously can it point at an object? And what does that data look like? And then also get some science for this kind of, pretty typical hot Jupiter, which are, these gas giant exoplanets that are the focus of many studies.
So one of the reasons that we see there's a little bit of a bias in the data, right, for finding hot Jupiters. They're big, they're bright, they can cover enough of their parent star's light that they come across in the data very, very easily. So finding those light curves works in our favor. What kind of star is WASP-43? Like what are we orbiting here?
Yeah, I can't remember the exact details of it off the top of my head, but it's like a K star, so it's colder than the sun, but it's still a fairly large and massive star. It's not one of these M dwarf, red dwarf stars that we hear a lot about. It's kind of in the middle between a sun-like star and a red dwarf. Yeah, and so that also helps it be more detectable because it's a smaller star with such a large planet, and it makes that ratio between the two more favorable.
All right, I want to welcome in people who are watching. So make sure you guys keep telling me that where you're watching from. We have people watching so far from Germany, California, New Hampshire, Sweden, and Poland. So welcome in, everybody. Give us a like and a subscribe, and make sure you share this stuff out when you do watch it. So Taylor, talk some more about what you learned about this planet. So I'm guessing because this is a less than 20-hour orbit and a big planet very close to its star, we're talking about a planet that is tidally locked. So the same side is facing its star all the time, right?
Yeah, that's the general idea, is that there's one half of the planet that is permanently facing towards its star and one half that's permanently facing away from its star. That basically means that the planet's equivalent of a day is equivalent to its year, and so it's somewhat similar to the moon orbiting the Earth, kind of a situation. Right. And so that heats the day side up to a very high temperature, and in the absence of any kind of heat transport, you would expect the night side of the planet to be extremely cold, potentially as cold as the cosmic microwave background, like tens of Kelvin or something like that. In practice, there's heat inside the planet from when it forms, and so that heats up the night side a little bit. But the biggest thing is that winds occur on any planet with an atmosphere. In general, nature dislikes gradients. And so if you have a really hot day side and a really cold night side, pressure will build up and push that hot day side gas onto the night side and kind of start churning up the atmosphere. And so, what we're trying to do with these observations is look at or get information about how those winds are transporting heat and chemistry things across the planet's atmosphere. So to do that, we observed a full orbit phase curve where the planet is observed for one entire orbit. And so we go from, at the start of this plot here, we're seeing roughly the day side pointing towards us, the observer. And then it passes behind its star and we see just the starlight only. And then the planet keeps rotating around. We start seeing the night side. And then the planet blocks part of the starlight. We see a big dip called a transit when that happens. And then we see it rotate back around to have the day side pointed towards us. And so we're doing this in mid-infrared wavelengths. In particular, we're using JWST's MIRI low-resolution spectrometer, which operates from about 5 to 12 microns. The data shown here are just 5 to 10.5 microns. And so these wavelengths of light, interestingly, are very similar to the wavelengths of light we use for non-contact thermometers, like you might see at a hospital. And so if you want to check someone's temperature and keep yourself healthy or whatever, you can measure wavelengths at this approximate region and see how hot they are. And so we basically use JWST as a gigantic long-distance non-contact thermometer to measure the temperature of the planet as it rotates. And again, we can't separately see the planet from the star. We see the combined light. And so what we get is this kind of curve. And if you kind of squint or you hold a straight edge up to your screen or whatever, you'll see that there's this kind of modulation to the signal. It's not just eclipse, transit, eclipse, but there's this kind of wiggling in the really, really long time scale wiggling. So it's hottest when we see the day side and faintest, coldest when we see the night side. And so, we can use that to, at all times, an entire hemisphere of the planet is facing towards us, as is kind of depicted here. So we go from seeing the day side to a little bit less of the day side and a little bit more of the night side, and we're constantly seeing combinations of these. And so we can do some math to try and convert that first plot that we saw into a curve, a plot like this, where we see what is the kind of temperature all across the planet. And so, yeah, when we did that, we found that the planet's dayside hemisphere average temperature is about 2,300 Fahrenheit, and the nightside average temperature is about 1,100 Fahrenheit. For those that prefer Celsius, that's 1250 Celsius on the dayside and about 600 Celsius on the nightside. And so, yeah, in doing so, in making these measurements, we got like a dayside measurement and a nightside measurement, but we also get some information about how that temperature map changes as a function of longitude. And so, yeah, by kind of combining all of this information, we can start to get some idea of what is actually happening in this planet's atmosphere. Yeah, where there might be clouds, and beyond this, there's also spectroscopic information. As I said, JWST operates, the MIRI instrument, LRS, operates from 5 to 12 microns. It's not just a single wavelength element for that whole range. There's many different wavelength elements, and so we split it up into, I think, about 14 wavelength elements. And so we could see how different colors of light have different phase curve amplitudes and stuff like that. And we can start to understand chemical species in the planet's atmosphere all across the planet.
So we have a tidally locked hot Jupiter going extremely fast with this huge temperature differential between the two sides of the planet. And so one of the things that you found is that the clouds, the weather, the winds are pretty wild here. So what have you learned about the weather going on with these temperature differentials?
Yeah, so talking about weather is a little bit complicated. In my brain, I interpret weather as, something that weather's one thing today, weather's another thing tomorrow. This measurement we made is technically, yes, just a snapshot of what the weather looks like at one moment. In reality, we expect it to change fairly little, and so it's more like a measurement of the average climate condition of the planet, or whatever. And we expect things to not really change much from one day to the next. And yeah, the findings that we found, that because the night side is so cold, we believe that there's some clouds on the night side that's kind of hiding some of the heat that would otherwise be radiated out from the night side. Yeah, different clouds act in different ways, but in general, we believe that these clouds are very high up in the planet's night side atmosphere, and that they kind of blanket the heat in, and so result in there being less heat radiated out from the night side. And so we don't know exactly where the clouds start and end or anything like that, but we think that probably most of the night side is cloudy. And it's possible that a little bit of the atmosphere, that kind of the night side, as it gets blown onto the day side, it might be a little bit cloudy and then eventually transition to something that seems to be pretty clear on the day side. And we also, because we have spectroscopy, we can also get another indication of that based on what molecules we see in the atmosphere. Because these clouds are so high up, they hide the molecules deeper in the atmosphere, and they kind of mute the signatures of different molecules in the planet's atmosphere. And so, yeah, all told, we think there's probably clouds on the night side. And related to, the temperature difference between day side and night side, and also the kind of chemistry on the day side versus night side, we think this planet has some ridiculous winds blowing from the day side to the night side. So I said nature abhors gradients, and it'll try and push heat from the day side to the night side. Because of this kind of synchronous rotation where the orbital period and the rotation period are the same, we generally think of the winds as flowing eastward, and models and data tend to suggest that happens. And so it's not just wind all flowing in one direction, whatever. Winds typically flow eastward from the day side over to the night side and then back onto the day side. These winds tend to be quite fast, and it's hard to estimate them, but from this paper, we estimated them to be about 5,000 miles per hour, or
I saw that.
8,000
That's
kilometers
not even
per
a
hour.
number like I think we can comprehend. Like
No.
it doesn't make any sense.
Yeah, it's 100 times faster than you drive on the highway, so that's just, yeah, insanely fast.
And so on top of that, so one of the things, of course, that JWST was designed for and has definitely become known for is this ability to determine the atmospheric composition. And there's a few interesting things going on with this atmosphere on top of these temperatures and winds. So what did you learn about the atmosphere itself?
Yeah, so the MIRI low resolution spectrometer on JWST is sensitive to a couple of molecules. It's sensitive at wavelengths where we might expect water to impact the spectrum. It's sensitive to the possibility of methane, and it's sensitive to the possibility of ammonia. Unfortunately, these data were kind of corrupted in the area where we might detect ammonia, so we couldn't really say much of anything about that. But we could really investigate the presence of water and methane in this planet's atmosphere. Water is one of the most abundant molecules in the universe. It's made of 2 hydrogens and 1 oxygen. 2 hydrogens together is the most common molecule in the universe. And then hydrogen, you just check a little bit of oxygen in there. So we expect water to be basically everywhere. Basically every planet, we expect to see water. The main exception is extremely hot planets. That water becomes unstable and you break off the oxygen and you're left with just hydrogen and oxygen separately. So we really expected to see water, and we did. And previous observations with the Hubble Space Telescope looked at a different wavelength that was also uniquely sensitive to measuring water. So that was just a nice confirmation. Yeah, there's quite likely water, and it's at about the level that we expect for a planet of this mass and radius and things like that, and temperature. Then the next most interesting thing is, what about methane? On the planet's day side, about 2,300 Fahrenheit, it's too hot for methane to form stably. So you have, you would expect no methane on the planet's day side, but on the planet's night side, it gets down to about 1,100 Fahrenheit. Which is cold enough that methane should just naturally occur just due to carbon bumping into hydrogen and stuff, and just atmospheric chemistry. We're not talking about life or anything here. It's just atmospheric chemistry. So we'd expect there to be methane on the night side. Mm-hmm. However, we found the lack of methane anywhere on the planet. So that was surprising. The kind of solution to that we came up with is called disequilibrium chemistry, where those winds that I was talking about, whipping from the day side to the night side, are transporting that methane-free gas from the day side, flipping it over to the night side, and then it's whipped back around to the day side too fast for those atmospheric reactions to occur and produce methane. And so those are the main things. The lack of methane would also suggest that there would probably be a little bit more carbon monoxide throughout the planet than might otherwise be expected, because that methane would break down probably into carbon monoxide. But though that molecule is not really probable with MIRI, and we'll need a different instrument to investigate that hypothesis.
So that is a lot to learn about one planet that is nowhere near us. I mean, that's actually incredibly impressive. So you know how big it is, you know how fast it's orbiting, you know a lot about its star, and now you know the temperature of 2 different sides of it, and probably how the winds are working to move the different atmospheric molecules around, and you know some things about the atmospheric composition. I mean, keep in mind, this is a planet in a completely different solar system. So it is very stunning the kind of data that JWST is returning. So for all of our griping about over budget, overrun, all of that, the data is amazing. So what for you has been the most exciting part of this research?
I think kind of just exactly what you're saying. My PhD work was focused on data from the Spitzer Space Telescope,
Mhm.
which offered us some really exciting findings. All kinds of things. It collected many phase curves like this kind of data set, but only at a single wavelength. It observed the TRAPPIST-1 planets and helped discover and confirm some of those. It was a really great telescope. But one thing it was really not designed for was studying planets. And so it was really not a very stable telescope. There's kind of a heater that would cycle on and off that would cause the telescope to jiggle, and that would cause all kinds of jaggedness in the data. And yeah, there's just a lot of things that made it really challenging to work with. And so I spent my entire PhD trying to figure out how to deal with that kind of ugly data for our purposes. We're trying to get data that's like 1% of the noise that Spitzer's introducing. And then so yeah, started work on this data set as one of the first JWST data sets that I got to work on. And I sat back when I first downloaded the data and I had to do a little bit of processing to get it from like the kind of ugly spectra pictures that JWST produces to get, like a light curve, kind of like that first image you showed. But I did, and there was like no visible noise. it was so easy, and so I think that's super exciting for studying smaller and colder objects, and getting long duration observations like these. I think JWST is so stable and produces such amazing quality data that yeah, we're going to get some really exciting new results in the next 1 to 2 decades.
It is. I mean, just what we've had in the last year and some months has been basically almost year and a half. It's been amazing. I mean, everything from the images to the exoplanetary data has been absolutely stunning, and I love everything that's coming out. I'm going to welcome in just a few more people, and if you have questions for Taylor, please feel free to put them in the comments. We are keeping an eye on them. I've only seen one, and it's kind of silly, and I will ask it, but we'll get to that in just a minute. So welcome in. We have people watching from Belgium, some more from California, the Azores, Louisiana. Hello, Ron. Argentina. So that's really, really neat. Thank you for joining us from all around the world today. We really appreciate that you're watching. Okay, so this is the silly question, and I'm going to ask it, and I'm dating myself because I understand the question, but I don't know if you will get it, so we'll see.
Oh,
Zap fan wants to know if you've ever listened to WASP, and if you are allowed to look at me and say I have no idea what that means.
Frankly, I don't know.
So in the 80s, and this is dating myself because I am not a young pup, there was a heavy metal band called Wasp. And
Gotcha.
so to answer the question for you, yes, I did back in the days when I was into hair bands, and we will let it go at that. So do you have like a favorite planet that you're studying right now? Is there anything new coming up for you? What's next on the plate of Taylor Bell?
Yeah, so I'm part of this team that does this guaranteed observation time team with kind of a similar, objective and mandate as this early release science program where, we get a lot of data early on, and we're working with a bunch of like people who built these instruments, so they really understand the instruments and they can help us understand the instruments and help teach the community how best to do stuff. So we've been getting through more and more of those results and publishing them. Just about a week ago, we had another paper come out in Nature on WASP-107b, which was very exciting paper as well. Yeah, we have another 2 that are basically accepted and published any day now. And so things are just flying out the door, a bunch of different planets. The focus of these observations are on planets that are either colder and or smaller than were previously observed with Hubble and Spitzer. And so that's important for a couple of reasons. Smaller planets are starting to work towards that direction of studying potentially habitable worlds someday. And colder planets, similarly, it's moving towards those more habitable worlds. But these colder planets are also exciting for multiple reasons. You start seeing more diverse atmospheric chemistry. So I was saying, like on WASP-43b's nightside, we expect it to be cold enough that methane should occur, but we don't. One other paper that I led about 9 months ago, I think, was on WASP-80b. And so in that one, we did find methane throughout the planet, both on the day side and on the night side-ish. And so that confirms this hypothesis that there should be methane at about these temperatures. That one was only about 50 Celsius colder. So that tiny change in temperature, the day side is only 50 degrees Celsius colder than the night side of WASP-43. So that change in temperature matters, but so does the mixing. And so you get all kinds of different molecules popping up. Yeah, really, really exciting stuff.
So someone is asking, and this is a good question. The planet sounds like a giant chemical reactor. Are there any plans to further observe and try and gather some more detailed chemical compositions from it?
Yeah, so for sure. In a perfect world, one would send a satellite and go, just scoop up its atmosphere and see what it's like. That's been a great tool for studying things like Venus, Mercury, Mars, all those, Jupiter. This planet's 280 light years away, so we have to do everything remote, which makes things difficult. We can only get so detailed with our understanding. But there are additional JWST observations already scheduled, and I think potentially even already collected. So yeah, we observed this phase curve with MIRI, and a separate team from the Max Planck Institute for Astronomy in Germany is observing another phase curve of WASP-43b using the NIRSpec instrument. Mm-hmm. And so that covers somewhere around 2 to 5 microns. And so in that wavelength range, you get another kind of feature of water. You get methane, you get carbon monoxide, you get carbon dioxide, you can find SO2, there's a whole bunch of additional molecules in that wavelength range. And so, yeah, I'm really excited to see what they'll find with those observations. I said we expect there's probably carbon monoxide. That's a really, really strong molecule, really hard to break apart. So expect that to probably be there, but who knows? Nature always finds ways to surprise us. And by studying the kind of combination of all of these different molecules, we can understand, and doing that not just in one place on the planet, but all throughout the planet, we can understand what chemical reactions are happening where and how fast those are occurring, and how fast the wind's mixing, where clouds are, stuff like that. So yeah, it's really, really exciting opportunity, and yeah, people will definitely continue studying it. And this paper too was only the first paper on this data set. It was kind of just a presentation of the data. There's already one other team that presented a new way of analyzing the data called eclipse mapping, where you get some latitudinal information on the day side, so how cold the poles are compared to the equator. And yeah, there's many more papers in prep studying just this one data set, and more data sets to come.
It is all very, very exciting, and I am excited for you. So congrats on this paper. Congrats on a blossoming career. Thank you so much for joining me here today. And thank you to our audience, of course, for watching us. I'd like to thank Patricia for watching from London. I would also like to thank Julia for the stars on Facebook. Thank you so much, Julia, as always. And just to remind everybody, the SETI Institute is a 501c3 nonprofit. We rely on your donations for programs like this to do outreach and bring these fantastic young scientists to you to explain all of this new amazing data we're getting from missions like JWST. And so as always, thank you for joining us. If you want to support us, head on over to SETI.org and click the Give Now button, and it's greatly appreciated. So thank you again, Taylor. And don't forget to join us next week. Off the top of my head, I'm pretty sure it's another exoplanet. And I cannot remember it. Oh no. Next week we're talking about asteroids. So there was a study done using a ton of AI machine learning, and we found a massive amount of asteroids. So it's going to be really cool. We'll be talking to someone from one of the institutes that looks into that. So thank you everybody for joining us, and we will see you here next week. Taylor, thank you again. Everybody have a fabulous rest of the week.